So, as promised, this week we're going to talk about Lenz's law in lab, and also in lab, we're going to make some connections between electricity and magnetism. You're going to look at a previous um, simulation that we did on charges and fields, but you're also going to look at another simulation that deals with Faraday's law of electromagnetic induction. So once you complete those two assignments, I also have a worksheet for you on Lenz's law, determining the direction of the induced current. And this lecture or this mini video basically shows you how to determine that in the direction of that induced current with a few simple rules for applying Lenz's law. So please watch the video, and after you watch the video, complete all of the contents in the week 14 module for lab. Now, Faraday's law indicates that an induced EMF and a change in the flux have opposite algebraic signs. So the physical interpretation of Lenz's law is this, okay? The induced current in a loop is in the direction that creates a magnetic field that opposes the change in the magnetic flux through the area enclosed by the loop. So the induced current tends to keep the original magnetic flux through the loop from changing, the consequence of the law of the conservation of energy. Now we're going to talk about applying Lenz's law. Now, as I've said before, Lenz's law tells us the direction of the current induced inside a conducting wire that is produced by a change in the magnetic flux. So, under which conditions should we apply Lenz's law? Now, in order to apply this law, we must satisfy two conditions. One, we have a closed conducting loop of wire, and two, there's a change in magnetic flux taking place. Now, if these two conditions are met, we're going to look at some steps to apply Lenz's law. Now, the first step says we need to determine whether or not the magnetic flux inside the loop is increasing or if it's decreasing. Okay, remember that our equation for the magnetic flux says that the magnitude of the magnetic field times the magnitude of the area enclosed by the loop is times the cosine of theta, where theta is equal to the angle between your area vector and your magnetic field, okay? And then step two says that if the magnetic flux increases, then the magnetic field produced by the induced current points in the opposite direction of the original magnetic field, okay? So these two steps are very important. Now, if the magnetic flux decreases, then the magnetic field produced by the induced current points in the same direction as the original magnetic field. Now, step three says that once you know the direction of the induced magnetic field, you can then apply the right-hand rule, where the thumb is in the direction of the current and the fingers go into the direction of the magnetic field, or they curl in the direction of that magnetic field. Now here I have a rectangular loop of wire, and this loop of wire is pulled to the right out of an external magnetic field that points out of the board as indicated by the dots here. Now find the direction of the induced current. So if I take my flux equation again, so I know that the flux, or that magnetic flux, is equal to the magnitude of B times the magnitude of A times the cosine of theta. So as I'm pulling this coil to the right, okay, I'm experiencing less and less and less of a magnetic field that's throughout this coil as I pull it to the right. So therefore, if that magnetic field decreases, then the magnetic flux will also decrease. So if you look back on the previous slide that we talked about, in step number 2, it said if the magnetic flux decreases, then the magnetic field produced by the induced current points in the same direction as the original magnetic field. Now, the original magnetic field here is out of the page, okay? This is out of the page. So if I take the fingers of my right hand and I grab a portion of this wire, so let's say I grab this portion of wire here. It doesn't really matter, because you'll see whether it's clockwise or counterclockwise. But if I grab this portion of the wire here with my right hand and I curl my fingers in such a way that they come out of the screen, I will see that my fingers are starting to point towards me and my thumb points in the upward direction like this. So this is these are my fingers, okay, coming out, all right, and then this is my arm here, and this is my thumb, okay. It's a bad drawing, but there it is. I can see that that induced current is going in this direction, so that means that the induced current is going in the counterclockwise direction. Okay, it would do the same thing if I grab this portion of wire. I would see that my fingers are coming around the wire out towards me from the screen, and that my thumb would be pointing towards the right in this case. Okay, so it's still going in that counterclockwise direction. So the direction of the induced current is counterclockwise. I've also left 3 more examples for you, and you'll be able to see those in D2L. So please practice those. If you have any questions, please contact me.